Hello, this is ET250, Lecture 5. Today we're going to cover some nodal analysis examples, and then what we're going to primarily focus on is how to solve a set of simultaneous linear equations using matrices. And so I hope to show you how this tool is useful when we're applying nodal analysis, because what you'll get is usually a set of like three equations, three unknowns, four equations, four unknowns. And to solve those by hand ends up being kind of tedious. And this is kind of a blind, just formulaic process of how would you just put it into your calculator and actually get an answer for multiple solutions, okay? Let's look at nodal analysis, but before we do, let's do a little review of this Nodal Ohms Law. So we have this Nodal Ohms Law here, right? And so imagine you have some resistor, you have some ground way over here, I don't know, wherever it is in your circuit, and you have, for example, the node voltage is 7 volts over here, and maybe you have it V9, just to give it a name. And then you have R and some random kind of label for I, okay? So remember that the node voltage, if I give you the node voltage here at this point of 7 volts, what it really means is that there's a voltage of plus to minus 7 volts relative from that node to ground. If I give you this V9, let's say it's not even a number, it's a variable, but still the voltage is from this node with the red terminal or positive terminal here down here of that value, same value. So this is equivalent statement, right? V9 at the node is the same as V9 plus to minus, same with the 7, okay? Now, let's say we want to write the nodal Ohms law for this guy. We could say I equals, and I put this bar here because I'm going to put here the node voltage at the tail, which in this case is 7, minus the node voltage at the head of the arrow, which is V9, over R. Okay, and so that would be my nodal Ohms law for this situation. Okay, and just to review, the nodal analysis technique combines nodal Ohms law with KCL. So that's our nodal analysis. Now, there's of course many ways to solve your circuit problems, but this is just one of the many ways. So let's dive into an example here. And let's see how we can use our new nodal analysis techniques to just kind of formulaically solve this problem. And I will go over like another way, just using your standard techniques to solve this. But let's just do the nodal Ohms law way first. Okay. So the question gives us this voltage here. We got 3 resistors, and it looks like these 3 resistors are 1 ohm, 1 ohm, 1 ohm. Okay. And the question asks, solve for Vs using our nodal analysis. So like I said, we want to apply nodal Ohms law to all your resistors, and we want to combine it with KCL. And KCL would be applied very well at that node. Okay, notice we have current directions labeled, and so let's just blindly follow the process. So if I apply nodal Ohms law to this first resistor, I would see that I1 is going to be the node voltage at this point here. Now be very careful. And it looks like this node voltage is Vs. And by coincidence it is, because this Vs happens to be the node voltage from here to here, right? There's no element here. But assuming there was an element here, the node voltage at this point is no longer Vs. So you just got to be careful. In this case, it's nice because the negative terminal of this Vs is actually touching the ground here. And so the node voltage here in this case is in fact Vs. So I could say nodal Ohms law I1 equals Vs minus the node voltage here, which in this case is V2 divided by R1. No problem, that's safe. I could go over here, I could say the node voltage for this second resistor is I2 is equal to V2 minus 0 over R2. And if I look at this third resistor, I3 is equal to node voltage V2 minus 0 over R3. Okay. We can also see that we have a simple KCL I1 equals I2 plus I3. So I have all this written out right here. Let's double check. I1 equals Vs minus V2 over R1, good. I2 equals V2 minus 0 over R2, good. I3 equals V2 minus 0 over R3, good. And then what I can do is because I have my KCL, just pop these in. So I hope you can see how the strategy of this nodal analysis is conducive to currents in KCL, okay? Okay, so what I'm gonna get is an equation now with just voltages because the currents kind of get eliminated, right? And so here's my nice equation. And if we look closely, it's actually one equation, one unknown. R1, 2, and 3 are just the value 1 in this case. V2 is given, and that's just 5. So now we just have an equation where we can easily solve it by hand. So the R1s, so I could bring the R1 over in case it was a non-unity number. Um, and then I can say, well, Vs, I just bring this Vt over, is just this equation. And I know this is kind of a little tedious putting all the variables in here, even though the values are so simple. But what I like about doing this is that you can see how the variables affect the final voltage. Like this is actually an equation for the system that tells you what is the voltage here. If I plug in the numbers and I get 5 plus 1 times 5 plus 5, right? And I get 15 volts. Okay, so of course, I never like to stop here and just go, okay, 15 volts, great, box the answer, move on. I always like to go back and make sure that this strategy is giving me the correct answer, or at least a reasonable answer. So let's look over here and let's see. If I have this as 15 volts, this is 1 ohm, 1 ohm, 1 ohm, and this is 5 volts here, does that make intuitive sense? Well, maybe we can use some other techniques to think about if this answer that we arrived at, just kind of like blindly following this nodal Ohms law strategy, makes sense. So what I see here is I see two resistors in parallel. So I have a plus or minus Vs, I have a R1, but I also have this R equivalent with these two resistors in parallel. I know this is 1 because that was given, and I know that these two are the same, so that means this is going to be 0.1/2 because these are in parallel, right? If I have two resistors exactly the same, they'll be half of the value, right? The other thing I notice is that this is 5 volts, and the question is this 15? Is that reasonable? Well, we recently learned about our voltage divider. We have two resistors in series at this point, and we have the total voltage across of 15 volts, or at least what we think is 15 volts. Does it make sense that 5 volts is divided correctly from that 15 based on these two resistor values? And I think so, because you essentially have a 1 ohm resistor and a 1/2. This is 1/3 of the resistance value from here to here. So therefore the voltage should be 1/3 of the voltage from here to here. And remember, I'm putting this as the ground, right? That ends up actually being the ground. So I'm actually very happy with this 15 volt number based on just a very quick kind of cursory analysis going another direction, right? Of course, you could also do current divider, right? You could say I2 equals, this current times the R equivalent over this, and then play some games. You could also fall back on your regular KVL, KCL Ohms law and just start grinding away and crunching that. You could collapse everything down into one resistor, right? Parallel, series, find this current, find this voltage, and then do a KVL, find this volt, it's just crunch, crunch, crunch. So there's a lot of ways that you can solve this, right? But this nodal analysis is just another way, and maybe there's some tricks that when you're practicing in these homework problems, that'll just make you faster, okay? So I hope this first nodal Ohms law example makes sense. But one thing I want you to be very careful of is identifying the node voltages. And I do want to highlight, while we're here, I want to highlight this example. So let's say we had a situation like this. Okay, very similar problem, right? Let's say we had this node voltage V2, we had this ground here, and we'll call this R4. So we have R1, R2, R3, and R4 in VS. And it would be very tempting to write, I've seen this mistake a lot, nodal Ohms law, I1 is equal to VS minus V2 over R1. Exactly the same as you've written here. And this would be wrong. The reason why it's wrong is because this node voltage is not equal to VS. What you should do in this case is go, no, I see that resistor, tricky Chang-Siu. No. This, we'll just call it a name. Let's call it, I don't know, V1 since we haven't used it. The proper way would be to do this. Nodal Ohms law I1 equals V1 minus V2 over R1, V1 minus V2 over R1, and then do some other KVL or something to see what V1 is in terms of Vs or some unknowns. Because what you might have here is a V4, and therefore V1 by KVL is equal to Vs plus V4, right? And we could do that loop. Let me show you how this loop came about. Remember, V1, if I call this a node, is really the voltage from plus to minus V1. Do you secretly kind of see this like a loop here? So look at this, minus V4, minus Vs, and then I can go all the way back to home, plus V1 equals 0. And if I just bring these over to the other side, I get this equation, right? So I hope you can see that in this case, V1 is not equal to Vs, right? Because I have this resistor or whatever element here that potentially has a voltage drop across it, okay? In that case, V1 would be the addition of these two voltages, okay? So these are all highlighted in those online quizzes. Don't check those out, but yeah. Don't make this mistake. Okay, let's keep going. So what we're going to look at is a more complicated nodal Ohms law example. And what we're going to do is we're going to end up getting 3 equations and 3 unknowns. And then what I'm going to do is take a tangent into this matrix stuff and show you how to use even our TI-89 calculator to solve for some of the unknowns here. And so let's just see, what is the question asking? So this question is asking, what are the node voltages V1, V2, and V3 given these values of the resistors and this current independent current source value? So what do we have? This is 1 amp, and it looks like all these are 2 ohms. And we have our reference here, good. And we don't know what V1, V2, V3 are, but we're going to look for them. And then recall V1 is like a measurement. What would be the measurement if I took a black here? What is that value? What is that value? And what is this value, right? That's essentially what we're being asked to solve for. Okay. All right, again, nodal analysis is the combination of KCL and nodal Ohms law. So let's look at node 1. And what I recommend doing is the first thing is putting all your arrow directions and labels in, make sure they're all the different numbers, right? I1, I2. You wouldn't want like I2 and I2 to confuse you. So we look at here and we go, all right, we got node 1, I1 plus I2 plus I3 equals 0, and because they're all leaving. Okay, good. On the next one, we would have I2 equals I4 plus I3 because this one's entering and these two are leaving. And then on the third node, we'd have IS coming in and I4. So IS plus I4 equals I5. Okay, and so that's here. Node 2 is I2 equals I3 plus I4. And over here is I4 plus IS equals I5. Careful, don't get your S's and your 5's mixed up. Okay, now going back to the first node, we can write our nodal Ohms law for these 2 resistors. So this one, I1 is V1 minus 0 over R1 equals I1. Perfect. I2 is V1 minus V2 over R2 is I2. Good, perfect. We got that equation, this next equation by plunking these into your KCL. So V1 over R1, I omitted the 0. I2 is this, so it's V1 minus V2 over R2 plus IS equals 0. Yay. Okay, let's go to the next one. So we already have our KCL, I2 equals I3 plus I4. And now we have 3 nodal Ohms laws that we can write. We've already written this one, so we don't need to do this one again. But we have these 2 that we can write, R3 and R4. So I3 equals V2 minus 0 over R3. Good. And I4 equals V2 minus V3 over R4. Good. Again, push all these in, and then we get this equation. I2 is V1 minus V2 over R2 equals I3 V2 over R3, omit the 0, plus I4, which is V2 minus V3 over R4. Yay. Okay, so we got 2 equations now, and let's get our third equation, right? So as a third equation, we have another KCL, IS, yep, I4, I5, good. And We already have R4. Now we just have to write R5, Nodal Ohms law. And so that's just V3 minus 0 over R5. Okay, and then plug that in. So the final equation is I for the I4 is V2 minus V3 over R4. Now the current here in this case is from the current source. So you don't no Nodal Ohms law for this one, right? This is not a resistor. But you already know what the current is. It's just IS, which in this case is 1 amp, right? Okay, equals I5, which is V3 over R5. Okay, great. So you could solve this by hand. And let's look at what we're given. We have 3 unknowns, 1, 2, 3, V1, V2, and V3. There it is, okay? And they're all kind of mixed into these equations. And you might go, oh, do I want to solve this by hand? It's kind of gross. Yes, sure, I know what R1, R2, and R3, and R4, and R5 are. They're all 2 ohms, right? And I know what IS is 1 amp. Yeah, but how do I begin? Right? Trying to solve this by hand. Yeah, I know I can solve it 3 equations for nodes, but maybe I don't want to do it by hand. We could, but can we use maybe some brute force, just math, just kind of algebra strategies that have been there for a long time and are a nice calculator, right? Maybe it can punch it out. Okay, so we're going to hold this example, explore some math strategies, and then come back to this example and see if it can be applied to this to solve our problem. Okay, all right, so let's take a little tangent and look at solving simultaneous equations. And like I said, yes, 3 equations, 3 unknowns by hand is tedious. Matrix algebra can be very helpful. Here's the idea. Simple algebra is pretty easy. Let's say I have ax equals y, where x is my unknown. Okay, so we're going to link x to like these v1, v2, v3. So this is a scalar case, which means there's just one variable, right? One dimension. Whereas this is like a 3-dimension case, right? Because I want v1, v2, v3. But let's look at a 1-dimension case, right? Where we have ax equals y. Let's say a is 5 and y is 10. You could easily solve for this, right? You could say x equals a inverse, whatever a inverse happens to be, times y. Well, in this case, if if a is 5, a inverse would just be 5 to the -1. You'd multiply it by 10 and you'd get 2, right? 10 over 5. Done, right? So that's pretty easy. That is basically the concept of this whole linear algebra technique. The complication is, how do I set it up? How do I set up this A matrix, this X matrix, this Y matrix? And I'll show you in the next few steps. Okay, but here's the idea. Solve for the A inverse, multiply by Y. That's all we're doing here, okay? Okay, let me do a simple example with 2 by 2. So we're gonna, instead of going right to this crazy example, let's just do a 2 equation, 2 an unknown example. So in this 2 equation, 2 unknown example, let's say I have 2 unknown variables, x1 and x2. So 5x1 plus x2 equals 24, x1 plus 3x2 equals 2. And let's say I'm like, I don't know what x1 and x2 are, but whatever values they are, they have to satisfy both of these equations simultaneously. And these are lines, by the way. So if these are lines, it's like where the 2 lines intersect, right? These would be like the coordinates, like the xy values, okay, if that makes sense, right? Okay, so if you have these 2 equations and 2 unknowns, how could we use our matrix math, like this guy here, to solve for x1 and x2? Well, I can kind of write a more general version of this. Look how I've written out the form: A11, A12, A21, A22, Y1, Y2. Now notice x1 and x1, x2 and x2 stay the same, right? So I hope you can pattern match and see A11 is the 5, A12 is 1, Y1 is 24, A21 is 1, A22 is 3, and Y2 is 2, okay? And so what I'm gonna do is actually, I'm gonna pull out this x1 and x2 so that it is by itself. It's actually pulled out, and I'm gonna write it like this, right? So the way it works, can you see my fingers doing this animation, right? That's how you multiply it in. So this x1 is multiplying by this one, and this x2 is multiplied by this one, and then we go to the bottom row, x1 multiplies this one, plus the a22 times this x2, okay? So these two are the same thing, all right? Okay, pause the video, see if this makes sense, right? But it's not too bad. Okay, what we're gonna call this is our A matrix, just like this, or sorry, like this. We're gonna call this expanded thing the X matrix, which is like this, and we're gonna call this Y matrix this one, Okay, so what we're going to do is we're going to fill in these numbers and find out what is the inverse, kind of like this 5 inverse, and then multiply it by y, just like we did here, to get the unknown x. All right. Okay, in Google, if you just Google like a 2 by 2 matrix inverse, you'll see this formula. You don't need to worry or memorize this formula. You just need to know it exists, right? There's actually a formula that solves for the inverse in a general way. It's like the equation, right? There's proofs on this. Don't worry about it. Just trust that this is the formula. And if you go to Google, you'll find it. Notice it's just you flip these and then flip the signs and then divide by this thing called the determinant. Like I said, don't like waste brain cells on knowing what this is unless you're very curious. Okay, all I got to do now is plug in these numbers that correspond to these values into here and see what A inverse is. Okay, and then once I get it, I'm going to multiply it by y, and I'm done. I get x. All right, so let's do it. Okay, so if I follow the pattern, A11, like I said, is 5, A12 is 1, good, A21 is 1, and A22 is 3. Y1 is 24, Y2 is 2, good, no problem with that. If I follow this pattern, A22 was 3, so that means the 3 goes here, in fact, for this inverse. A11 is that 5, good. And then these just are the same values, just with flip signs. So this is 1 and 1, so it becomes -1, -1, good. Over here, if I follow this formula, A11 is 5, A22 is 3, good, minus A21, which is 1, and A12, which is 1. Yay. This is nice. This is an easy thing. 1 over 14, 15 minus 1. And this is 3, -1, 5. When I see the scalar, this outside, it means I can multiply every single value by 1 over 14. Okay, so if I take this and multiply it by that, I should get my final x. And let's do that. So I have 1 over 14 times this. That's my A inverse times this. And it's the same way. When you matrix multiply, you do this, like my animation here. So I'm going to take 3 times 24 plus -1 times 2. That's the top value. And then I'm going to take -1 times 24 plus 5 times 2. Okay, and that's this one. 3 times 24 plus -1 times 2. -1 times 24 plus 5 times 2. No problem. This is just a simple matrix multiplication. This 1 over 14 goes into everything. And what I get is, well, it looks like I'm breaking it down a little slowly. 72 minus 2, yeah. And then I get 70 minus 14. So I'm doing this very slowly. And I get 5 and -1. So what is that saying? My x vector is 5 and -1, but the first value of it is x1, and the second value is -1, because that's how I set up my x1 and x2. So this is the answer. x1 is 5, x2 is -1. Okay. Let's see if we could do this by hand. But even before we do it by hand, I suppose we could just check real quick. Did this answer satisfy these simultaneous set of equations? So x1 is 5. So 5 times x1. What's x1? 5. 5 times 5. Let me put this over here. 5 times 5 plus -1. What does that equal to? 25 minus 1. Oh, yeah. Nice. Okay, x1 is 5 plus 3 times -1. What does that equal to? Well, 5 minus 3 is 2. Oh, yes, 2. Nice. Okay, so this is good that we know that these numbers satisfy this. Could we do this by hand? We totally could do it by hand. Let's do it by hand, right? So if we have these equations, right? What you can do is you could solve for x1. I mean, there's so many ways to do it by hand. You could like multiply this whole thing by 5, subtract, and then solve for x2. Or you can solve this for x1 and then plug x1 into here, then solve for x2. And then once you have x2, plug it back in here, solve for x1. Let's just do that. So x1 equals -3x2 plus 2. Yeah, okay, no problem. I plug it into the top one. 5 times this answer is -3x2 plus 2 plus x2 equals 24. Good. Now it's just a matter of crunching. So, okay, solve one equation, one no problem. Okay, -15x2 plus 5 times 2 is 10 plus x2 equals 24. Good. Isolate the, bring the x2's together. So I get -14, then bring the 10 over 14. So it looks like x2 is going to be -1. Is that what we got here? It is. Nice. So we're seeing consistency. Once I have the -1 for x2, I just plug it right back in this equation. -1 times -3 is 3, plus 2 is 5. Boom, boom. We have everything that matches. So yes, you could do this right by hand. For a 2x2, maybe that's easy enough, right? But this is just, how do I say, a kind of a blind brute force way. If you don't even, you don't want to like do it quickly, you're just like, I don't care. Just give me the answer, punch it in. Well, this will give you an answer. It's just like a formula, okay? So let's keep moving on, and let's not get lost in the sauce, right? What are we doing? We're trying to solve this 3 equation, 3 unknown. We're trying to use this little algebra technique that is kind of a brute force way. And let's see if we, we can do this without having to be tedious with the hand calculations and let the computer do the work. Okay, so let's say we want to solve a 3x3 matrix. So what we can do is use a matrix solver to find A inverse, MATLAB, a calculator, Google. These all give you the inverse, right? We just need to get it into this form. So the hardest part is actually getting it to the form. Once you get in the form, it's punching the calculator is easy. Okay, so I'm going to rewrite the 3 equations that we got. Okay, so let's go back here. So we have, good, v1 blah, 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 over r1 plus v1, blah, okay, yes, v1 minus v2 over r2 equals v2 over r3 plus v2 minus v3. Okay, good. v2 minus v3 over r4 plus is equals v3 over r5. Great. Great. So we have everything rewritten. So now we look here and we go, well, what was our unknown again? Our unknown was v1, 2, 3. So now x is not just x1 and x2, it's v1, v2, v3. And A is anything attached to the V's or X's. So these 1 over R1s are going to be essentially what build the A matrix. Now anything left over, anything not attached to these is going to go to the other side. That's going to be like the Y's, if that makes sense. All right. So let's move to the next slide. And what I'm doing is I'm rewriting this equation. So on the left, it's everything where I have something attached to the V's. And I'm going to put on the right side anything that's not attached to the V's. So for the first equation, it's V1. And notice I've actually even done another step. I've put the V1s together, right? Because this is V1 times 1 over R1 plus 1 over R2, extracted that out. Okay, the V2 I have minus 1 over R2. And for the V3, I do have to have it, but I got to pad it with a 0 placeholder because I don't have any V3. And then this IS is just going to go to the other side. So I have negative IS because it's a leftover. Okay, let's see about this one. Is there any leftovers on this one? No leftovers. So the right side is going to be 0, but the left side is all my V stuff. So I'm going to bring these two guys over. Okay, so let's do that. So if I bring it over, I get, let's double check, V1 over R2, good, I have that. Now V2, look, I have it in 3 places. So I have a minus 1 over R2. When this comes over, I'm going to have a minus 1 over 3. And when this comes over, it's going to be minus 1 over R4. Good, minus 1 over R2, R3, R4. Now what about V3? In this case, I have a minus 1 over R4 on the right side, but if I bring it over, it's going to be a positive 1 over R4. Excellent. And again, no leftovers. Now, if I squash this down one more time, I get V1 times this, but then I'm going to smash all these things together. Negative 1 over R2, blah, blah, negative 1 over 3, negative 1 over 4, okay? Okay, this is my second equation, and then I got one more equation, that's this guy here. And I go, okay, well, in this equation, looks like this is going to be my leftovers again. I'm going to pull it to the right, I'm going to pull this to the left. Is there any V1? It looks like there's no V1, so V1 times 0, okay? And then like, well, I had an intermediate step. V2 is going to be just 1 over R4. V3, I have a negative 1 over R4 and a negative 1 over R5. And then it's going to be negative 1 over negative IS on the right side. So yes, 0 placeholder for V1, 1 over R4 for V2, and then the negative 1 over R4, negative 1 over R5 for V3, and then the minus IS. So here I have my 3 equations, 3 unknowns. And now it's very close to that AX equals Y form. And this is what it would look like. This is what that AX equals Y form. So X is V1, V2, V3. Okay. And let's look at this A matrix. Notice the A matrix follows exactly what we got here without the V terms. 1 over R1 plus R2 minus 1 over R2, 0. 1 over R2, this guy here, 1 over R4, good. 0, 1 over R4, this guy here. Not too bad. And then the Y is easy. It's just negative IS, 0, negative IS. Boom. So all you got to do is punch this in your calculator, hit the inverse, and then multiply it by this guy. And at this point, all of these are numbers. Remember R2, I think, was like 2, and IS was like 1 amp. Okay, so now we punch all these in your calculator, and that'll give us these unknown values. So like I said, the hardest part was maybe setting this up and just making sure that, you know, your bookkeeping is correct. You're not missing your signs or anything. But after that, it's blind, right? You just let Google or your calculator do it. Okay. We can remember ours too. This is the steps of how you would do it. And now I'm going to show you how to do this on your TI-89 actually. So here I'm putting all the values in, and this is actually the A matrix that I get when I plunk in all the values, right? Now, if I take this and I go into Google and hit the inverse, like punch this in and then go hit A inverse, I get these numbers, right? You don't care what these numbers are. These are just the numbers of the inverse, okay? And when you have this, you just multiply it by Y, like I said, -1, 0, -1. And then you see what you get. So when I take this matrix and multiply by this, remember, I'm taking this and multiplying here. So 1.25 times -1, good. And then I'm taking 0 times -0.5, so that's gone. And -1 times -0.25 here, that's this one. So it looks like from this solution, it doesn't actually care about the middle column here. So again, next one, -1 times 0.5, good. 0, yep, -1 times this, that's here. -1 times 0.25, 0, -1 times there, good. Add these up and I get my three values of V1, V2, V3. Okay, so this, when I add it together, I get -1, I get 0, and I get 1, okay? Okay, so this was it. This was the answer. -1, 0, and 1 volt. Does that make sense? Let's see if that physically makes sense. Let's check the physical. Actually, you know what? Before we check if this makes sense, let me just show you how to do this on the TI-89, and then we'll go and see if physical intuition is matched. Okay. Let me pull up this one here. So on your TI-89, this is the syntax, okay? This is the syntax. And the syntax is like, you know, what is the low-level way you're just gonna punch in this, this formula here, right? So what you can do is, if you wanna type in the A matrix into your TI-89, this matrix here, so 1, -1/2, 0, this is the way you would type in the first column. You would have hard brackets, that's like the entire matrix. And if I want to put in the first column, I put 1, -1/2, 0, semicolon, 1/2, -3/2, 1/2, semicolon, 0, 1/2, -1, hard bracket. So that actually is A. If I want to do the inverse, I do a little caret for the hat, and then I put in a -1 for the inverse. So that actually gives you this number, okay? So this and these are the same thing, good. Once I have this, I can do a multiply times Y. So Y is also a matrix, but Y is -1 colon or semicolon 0 semicolon -1, right? And when I punch this into MATLAB, or not MATLAB, but my calculator, I get -101, which is just this. Okay, let's do it. So what do we have here? So I have my hard bracket. So if I look on my TI-89, let's find the bracket. So if I look carefully, I see it right here, but I have to hit the second key. Okay, so 1, -1/2. Now be careful, it's not this negative, it's this one, because this is the minus, this is the negative. So -1/2. If you do this one, it'll complain at you. So -1/2, 0, okay, good. Now I hit the semicolon, you gotta be careful. I think it's the second and then this 9, because that's where it is. Okay, good. And then it's 1/2 again, and then -3/2, and then 1/2. Okay, so that's this, good. And then semicolon, now we're on the third row, so 0, comma, and then 1/2, comma, -1, and then I finished it. So that's actually, oop, did I make a mistake? Let's double check here. So 1, -1/2, 0, good. And then I have 1/2, ooh, I think I forgot the comma there. -3/2, 1/2, good. And then 0, 1/2, -1, good. Okay, so that's my A matrix. That is this guy right here. And we can even see now it's printed in pretty if I got everything in there correctly. Good, I'm happy. So if I want to find the inverse, I can just go to the -1, okay? So that's actually this guy. Does that make sense? 5/4, 1.25. Yeah, that sounds right. -1/2, good. -1/2, oh, 1/4. Yeah, these all these values look correct. Okay, so now I can take that. So I have my inverse here, and I can multiply it by the y, -1, semicolon, 0, semicolon, -1, hard bracket, and -1, 0, 1. Boom. Not too bad. Pretty painless, right? All in your portable, nice TI-89, right? Okay, so I hope that was pretty helpful. Okay, let's go and make sure that these numbers make physical intuition match, right? We can actually not take a step and actually plug these numbers actually into the equations and see if that matches. So we had these nice equations here, right? This is all the way at the beginning. So let's go back to the slide. Here we go. Yes. Okay. So V1 over R1. So if we plug in -1, 0, 1, which is V1, V2, V3, so that means V2 is 0. So V1 is -1, right? So we get -1 over 2 plus -1 over 2 plus 1. Oh, we have -1/2, -1/2 equals -1. They cancel. Excellent. Okay, that's good. Let's go to this one. All right, so if we go to this equation, we go, okay, so that's 0, that's 0, that's 0. So this is -1, this is 1. What do we have? -1/2 plus -1/2. Okay, -1/2 cancels with -1/2. Yay, we're good. Okay. All right, what about this one? Number 3, let's go to here. If I have -1, 0, 1, so this is 0, good. This is 1, so this becomes -1/2. This is 1, so we get -1/2 plus 1, good. And then on this side, we have 1/2, good. All right, so we got -1/2 plus a 1, which ends up being a half. And then does this match another half? It does. Fantastic. So that's really good. But again, that didn't really, ping our intuition. This just showed us that the equations were happy. I'm like, well, let's just look at the intuition first or last, right? So we have -1, 0. So that's saying this voltage is -1 volt relative to here. We have 0 volts relative to here and 1 volt. And the question you might ask is like, what does negative voltage mean relative to here? Huh. Well, what it's saying is, let's say we had I don't know, maybe the best way to say it is, let's say here's a house, okay? Yeah, traditionally we think of this as the 0, right? This is the ground level, right? And so maybe you have a basement, right? And so let's say this, you could think of this as 1 level, right? Plot positive. And maybe here you could think of as -1 level. Maybe that's the easiest way to think of, like, what does it mean to have negative voltage, right? Maybe you could think of it like a battery. Here's a battery with a plus and minus, right? Well, sure, usually you think of this as 0, but what if you thought of this as 0? Well, then this point relative to here becomes -1.5 volts, right? So hopefully that kind of clarifies what that means, being -1, all right? So then we look at this and we go, okay, -1, 0, and 1. Okay, does that make physical sense? Well, we have 1 amp flowing from here to here, and it looks like all these resistors are the same. And if I look at the physical configuration, they look symmetrical, right? You see, 2 resistors here, 1 resistor here. So that tells me that this voltage here is going to be in between the value of these voltage, kind of like a voltage divider principle, right? And because these resistors all perfectly symmetrical, this voltage is going to be exactly the same height above as this voltage is below the center point. And that does happen to be the case because this is 1 and -1, and that's 0. That's good. Okay, does it make sense that this is the higher voltage and this is the lower voltage? I think so too, because current is being forced to flow this way. So remember, all these resistors are acting like rusty pipes. And so you're going to have a higher pressure here and a lower pressure there. I think that makes sense. So I hope this lesson showed you a nice tool on how to solve this using nodal analysis, using math and matrix algebra to solve simultaneous equations of like 2 equations, 2 unknowns, 3 equations, 3 unknowns, and more. So it doesn't, you're not just limited to 3 by 3. You could have 1,000 by 1,000 if you wanted to. And I also hope it also backed up your physical intuition with your circuit analysis. Anyways, thanks for paying attention, and I'll see you in class.